somewhere on Earth right now, inside a stainless steel chamber about the size of a beer keg, bolted to a laboratory floor in a building you could drive past without a second thought. There is a cloud of a few thousand atoms that is colder than anything else in the observable universe. Colder than the vacuum between galaxies. Colder than the night side of Pluto. Colder than the leftover glow of the Big Bang. Nature has had 13.8 billion years and 100 billion galaxies to work with, and it has never once produced a temperature this low. Human beings did it on purpose, in a basement, and they have been getting better at it every year since. Here are the numbers, because the numbers are the whole story. The coldest naturally occurring place astronomers have ever measured is the Boomerang Nebula, a vast cloud of gas roughly 5,000 light-years from Earth, blown outward at enormous speed by a dying star. As that gas expands, it cools, the same reason the nozzle of an aerosol can go cold in your hand. And it has cooled to about minus 272 degrees Celsius. 1 single degree above absolute zero. That is the coldest natural place ever measured anywhere in the universe. Ordinary interstellar space, far from any star, is warmer, around minus 270 degrees Celsius, held there by the cosmic microwave background, the faint radiation left over from the birth of the universe, stretched and chilled by billions of years of cosmic expansion, and still, stubbornly, warm enough to matter. Physicists in a laboratory blew past both of those numbers in 1995, and they did not stop at 1 degree, or a tenth of a degree, or a thousandth. Routine experiments today reach billionths of a degree above absolute zero. The standing record is 38 trillionths. Written out, that is 0.00000000038 degrees above the coldest temperature physics allows. Nature, across the entire observable universe, has never gotten as cold as a basement in Colorado. Absolute zero, minus 273.115 degrees Celsius, is not really a temperature. It is a flaw. It is the point at which atoms have surrendered all the energy they are permitted to surrender, where motion drops to the irreducible minimum quantum mechanics allows. For centuries, physicists assumed it could be approached but never touched, and they were right, for a reason that turns out to be built into thermodynamics itself. Every cooling step removes a fraction of the remaining energy, never all of it, so reaching absolute zero would take an infinite number of steps. Absolute zero has never been achieved, and never will be. What matters is what shows up on the way down. Because, at a few billionths of a degree, matter stops behaving like matter. Atoms stop acting like separate particles, rattling around in a container, and collapse into a single collective object, sometimes called a superatom. They all occupy the same quantum state, share the same energy level, and become genuinely indistinguishable from one another. Not hard to tell apart, but with no individual identity left to distinguish. This is a Bose-Einstein condensate, and it is a state of matter that does not exist anywhere in the natural universe, because there is nowhere in the universe cold enough to make one. The prediction came first, by 70 years. In 1924, an Indian physicist named Satyendra Nath Bose sent Albert Einstein a paper about the statistical behavior of light particles. Einstein saw that the same mathematics ought to apply to atoms, extended the work, and published in 1925 the claim that at sufficiently low temperatures atoms would pile into a single quantum state. Then the idea sat there, unreachable, for 7 decades, because nobody had any way to get within a billionth of a degree of absolute zero. The tools arrived in the 1980s, and they arrived from a different direction entirely. Stephen Chu, Claude Cohen-Tanuji, and William Phillips developed methods for slowing and trapping atoms with laser light, work that won them the Nobel Prize in Physics in 1997. Once those techniques matured, nanokelvin temperatures went from impossible to merely extremely difficult, and a genuine race began. Eric Cornell and Carl Wieman, working at GELA in Boulder, Colorado, got there first. On June 5, 1995, using rubidium atoms cooled to 170 nanokelvins, 170 billionths of a degree above absolute zero, they made the first Bose-Einstein condensate. They proved it with a photograph, a sharp spike rising out of the center of a diffuse cloud, the visible signature of thousands of atoms abruptly behaving as one. That image is now one of the iconic pictures in modern physics. Months later, Wolfgang Ketterl's group at MIT did it with sodium atoms and produced a far larger condensate, then went on to build the first atom laser, a coherent beam of matter, the quantum equivalent of an optical laser. A third team, led by Randall Hewlett at Rice University, was chasing lithium condensates on almost the same timeline. Cornell, Wieman, and Ketterl shared the 2001 Nobel Prize, which means the condensate took 2 full Nobel-winning generations to reach. One to build the instruments, the next to use them on a threshold Einstein had described in 1925 and never expected anyone to cross. The cooling itself sounds backwards. Lasers heat things. That is the entire point of a laser cutter. But if you tune a laser very precisely and fire it at a cloud of atoms from 6 directions at once, an atom moving toward one of those beams will preferentially absorb photons coming head-on, and each absorbed photon delivers a tiny momentum kick against the direction of travel. Do that millions of times a second from every side, and you get what physicists call an optical molasses. The atoms are not pushed anywhere, they are simply unable to move. That gets you to millionths of a degree. The next stage is evaporative cooling, which is exactly what it sounds like. You loosen the trap and let the fastest, hottest atoms escape, the way a cup of coffee cools by losing its most energetic molecules until only the slowest remain. Magnetic fields and radio waves handle the final push into the nanokelvin range. You start with billions of atoms and finish with a few thousand, because everything else has been thrown away for being too warm. Here is the detail that almost never gets mentioned when those record numbers get quoted. There is no thermometer. There cannot be. A thermometer is an object at room temperature, and room temperature is about 10 billion times hotter than the cloud. Touching it with anything solid would be like measuring a snowflake with a blowtorch. The atoms sit in a vacuum harder than interplanetary space, suspended in magnetic fields, in contact with nothing at all. A single stray air molecule at room temperature wandering into the chamber would blow the condensate apart. So temperature here is not measured, it is inferred. The trap is switched off, the cloud is photographed as it drifts apart, and the rate at which it spreads tells you how fast the atoms were still moving. Temperature, at this scale, is a statement about the velocity spread of a few thousand atoms. And the coldest of these states lasts seconds. The coldest place in the universe is also one of the most fleeting things ever created. Which brings us to the strangest part of the record. On Earth's surface, gravity is the obstacle. Gravity pulls the cloud downward, so you need relatively strong magnetic fields to hold it in place, and strong fields agitate the atoms and set a floor on how cold you can go. The trap becomes the thing that stops you. The only way past it is to remove gravity from the experiment, so physicists started dropping the experiment. A team based at the University of Bremen in Germany reached 38 picokelvins by dropping the entire cooling apparatus down the Bremen drop tower, a 120-meter free-fall shaft, where a much weaker, gentler trap was enough to hold the atoms in place. In freefall, nothing pulls the cloud anywhere, so almost nothing has to hold it. The idea was permanent by 2018, when NASA installed the Cold Atom Lab aboard the International Space Station. The station is itself in continuous freefall, so condensates made there hover indefinitely, unconstrained by the planet whose physicists invented them. To build the coldest place in the universe, we had to get off the Earth. And the reason was not the vacuum or the darkness of space. It was to get away from our own gravity. All of this effort exists to make quantum mechanics visible. At ordinary temperatures, quantum behavior is drowned out by thermal noise, the way a whisper is drowned out by a stadium. Superposition and entanglement are there, but buried. Strip the energy out, and the whisper becomes the only sound in the room. Atoms stop behaving like billiard balls and start behaving like waves, spreading, overlapping, interfering with each other, occupying multiple places at once in ways you can photograph. An ultra-cold lab is essentially a microscope pointed at quantum mechanics itself. The most theatrical demonstration involves light. In 1999, the physicist Len Howe and her team at Harvard sent a pulse of light into a sodium condensate and slowed it from 300,000 kilometers per second to about 17 meters per second, slower than a bicycle. A few years later, they stopped it completely, parked the information the pulse carried inside the collective quantum state of the atoms, held it there, and then released a working pulse of light. Back out on command. Light was brought to a halt, stored as a pattern in a cloud of atoms, and handed back. That technique is now a standard tool for studying how information behaves inside quantum matter. The payoff has already reached your pocket. Atomic clocks, the most precise instruments ever built, depend on laser cooling. The best of them use ultra-cold strontium and would not lose a second over the entire age of the universe. GPS runs on that precision, because a timing error of a few nanoseconds becomes a positioning error of meters on the ground. Quantum sensors built from ultra-cold atoms can measure minute variations in gravity, which means detecting underground water, buried structures, or the movement of magma beneath a volcano from the air. And quantum computing, still early, depends on exactly the fragile quantum states that ultra-cold labs exist to study. It ultra-base. So the coldest place in the universe is not out there somewhere in the dark between galaxies. It is a steel can in a building with a parking lot. And it is colder than the dark between by a factor of 10 billion. The universe is full of extremes we can only look at from a distance. The pressure inside a neutron star, the heat of a stellar core, the vacuum of intergalactic space. Cold is the one extreme where we stopped observing and started competing, and won.